of the brain. This one is PET, which is positron emission tomography, and this is showing the metastases of a tumor. And finally, this is just your normal X-ray image. So that's a human elbow from 2 points of view. So obviously, all these different techniques, which are called modalities, they're used for different purposes. And the one I'll talk about is CT. So specifically, this is X-ray computed tomography, and it's called tomography because it produces slices. That comes from the Greek word tomos, slice. And here we have a commercial CT scanner. So you've got your source, your detector, and the patient would lie in the middle. Now, from this point, you will take one image, and then you would move this whole thing. You would move the source and the detector. You would change the angle, and you would take another image. And that's called a projection image. Projection. So in this case, this is the mouse. This is the upper body of the mouse from one point of view. Now, if you take, say, 100 or even more projections from different angles, you can then reconstruct a three-dimensional data set. And this is what CT does. It's been invented in the 1970s, and from then on, it developed into various subgroups of medical imaging. I'll be talking about spectral CT in this case, and I'll explain how that is different. But first, this is what CT slices would look like. So one data comes off the scanner. It would look something like this. You would have slices, say, through a head, like so. But of course, you can also slice in different directions, so like that, or like that. And finally, which is the new approach, that's the three-dimensional visualization. And most viewers which you can get, so all commercial and free viewers would normally support views like that. And of course, I'm studying visualization of this sort. Now, CT is used in medicine, obviously, but also it's used for materials testing. So if you want to look inside an object without destroying it, you might use a CT scanner. Or for things like looking inside fragile Egyptian mummies. Once again, you don't want to cut it open, so you can scan it. Now, CT unfortunately has a few limitations, and of course, this is quite a bad feature, and this is ionizing radiation, which means it causes cellular damage, might give you cancer. And something like from 0.5% to 2% of all cancers in the US, depending on which study you look at, are now caused by CT exposure, X-ray exposure. Now the other point is that sometimes you need, well, half the time, you need to inject contrast agents, which are basically just chemicals to make certain things visible. So blood vessels or your digestive tract become a little better visible if you inject a certain chemical into the body or get the patient to eat that chemical. And of course, these are sometimes quite nasty chemicals, and you might have an allergic reaction. Yeah. Especially if your kidneys are failing, that's even worse. Now also, CT is basically like black and white photography of the human body. So you measure just the total attenuation. You measure how dense something is inside the body. So obviously, bones would be dense and soft tissue less so. And that's how you discriminate between tissues. And yeah, the final point is just that you can get nicer looking images by giving the patient a higher dose, which is obviously not something you want. So there are other ways to improve CT aside from giving people higher dose, right? This is your standard CT, so one source, one detector, and one volume, which is what you get at the end. And this is quite useful, of course. This is what all commercial CT scanners do. And now a new development is dual energy CT, which is basically two sources, two detectors. And of course, something like twice the dose. You get two volumes, and then you might be able to get some sort of more detailed information about what's inside the human body. But spectral CT, and this is what the Mars CT scanner does, is it uses one source, one detector, but it produces multiple volumetric datasets, which we call energy bins. And that allows us to basically see a color image of the inside of the body. Now this is quite a big advance in CT imaging. So this is what it is. Basically, CT, spectral CT, measures different sub-ranges over the whole X-ray spectrum. So think of them as color channels in photography. So these might be your red, green, and blue channels. And they will all have slightly different information about what's inside the object being scanned. Which is, and it works because materials, so different chemicals, respond to X-rays of different frequency. And so if you measure that frequency separately, as opposed to just having one range, which is what normal CT does, if you measure that separately, then you will get a lot more information. And this is what the Mars CT project is doing. We're developing the world's first spectral CT scanner. And yeah, the word Mars stands for Megapixel Resolution System. So unfortunately, this is not about going to Mars. But yes, this is it's basically about, let's say, the size of this table, made of lead, for obvious reasons. And then you will have your source and detector here, and the sample will go in the middle. So currently, this is what is called micro CT, and it's used for preclinical imaging, which basically means we have to image small animals like mice or pieces of human tissue. And we do that because we have to prove that this technology is safe and useful. This brings together physicists, doctors, biochemists, and even some computer scientists like me. Now, inside of this are the Metapix detectors, and those have been designed by CERN, which obviously is the same organization which built the Large Hadron Collider, and those chips are also used in there. And we have a license to use them for medical purposes. But because it is such a novel idea, we don't have the software for it. So the Mars project has to design all of its own software, which is basically acquisition, so how you get the images, processing, because the images are often quite noisy, so that's basically to clean them up, make them look a bit nicer. And then this is actually the important part, reconstruction, so that's turning projections from multiple angles into volume data. And currently we use a process called algebraic reconstruction, which in fact is written by Niels, who did not come to the seminar, but he's sitting just there. Now, visualization, that's what I do, and specifically, of course, 3D volume rendering. So now I'll talk a bit about just what this process is, and then you will see the results. So here is an example of a single slice through a mouse's abdomen. Now, these are the different energy pins, so these are your color channels. They describe the same physical slice through the mouse, but you see slightly different things. Because, as I've said before, materials respond in different ways. And if we visualize all these 4 volumes in 3D separately, you can see the results. So this is 1, 2, 3, 4. And so you can see how when it gets to the 4th energy bin, you basically can't see the bones anymore. But what you can see is you can see the barium, which which they fed the mouse. So this is an example of a contrast agent to make something very dense and appear on CT. Now, I'll describe the process which turns this volume data into images like that. So here we have a bunch of images which would normally come just as a single bitmaps or TIFF files, in our case TIFFs, and we would stack them. On top of each other and form a volume. And now through the process of volume rendering, and specifically volume rate casting, which is a subset of volume rendering, we get an image. And the way it works is you would cast a large number of rays into your volume from a certain point of view. Now, these rays, they would go into the volume, so you cast as many rays as you have pixels in your image. So they go into the volume, and they sample inside. Now, at every sampling point, you get the interpolated density value. So you get this grayscale value, and you then turn it into color and opacity by using a mapping, which I'll demonstrate in a second. And basically, you would sample something like 100 or even 500 times per array, which might mean that you end up with billions of samples per second. So it's not a difficult process, but it's a computationally intensive process. Now, this is an example. But here, I have a tooth. So suppose you've scanned it, and you've got these slices here. So the bottom slice would be a slice through here, then this one through here, and so on. So you've got a volume of these slices. Now, you would cast rays into this volume, which would sample in different places. So say, if your ray samples here, you can design a transfer function in such a way as to say, this should be completely transparent. So this is air. You don't want to see that. And that's why you see nothing around the outside. But then if you sample in here, which is the tooth itself, then you can give it a different color. Like this here. And then of course, this is a very basic transfer function. This is just a black and white mapping. But they're actually very powerful things. And so what you can do is you can design a transfer function to make certain parts translucent, and you can see what's underneath. And of course, it just looks cool. So this is the process that we use, and in effect, all the images that I'll show you now have been acquired using the Mars CT scanner and visualized with the software that I'll talk about later. So this is the inside of the crab's shell. With some dense structures. This one is quite an interesting one, in fact. This is gold nanoparticles have been injected into this mouse, so into the veins. Now, this is important. As you see here, you can see the kidneys, because these gold nanoparticles, in fact, concentrate in the kidneys and act as a contrast agent. So you can now see the structure of the kidneys, which you normally would not be able to see in a CT scan. And then this is the same mouse, just scanned just the pelvis and the lower spine. And we have the cow bones. So this is the bone and cartilage, which are made to look like a slab of meat. So you can see how, in fact, volume rendering allows you to get very detailed images. So you can see the structure of the bone. And in fact, even the structure of the cartilage. See these little grooves here. So, okay, now I've covered sort of the basics of visualization, but in fact, I still haven't said how exactly we're using this kind of visualization for spectral CT imaging. And for that, I'll use one example. So this is atherosclerosis. This is what a lot of people in the Mars project are looking at. And we believe that we can use spectral CT to better diagnose it. Now, in fact, it's a complex condition. So it's not like the popular perception of somebody eating a fatty hamburger and then that fat being deposited on the insides of your arteries. That's not quite what happens. What actually happens is that over time, and due to your diet or smoking or in fact even your genetics, you get a buildup of dead white blood cells in your artery walls, which of course, as many years pass, lost blood flow. And what's even worse, bits of the plaque, well, it's called an atherosclerotic plaque, bits of the plaque may break off, and in this case, go into the brain, and can cause a stroke. Now, it's a very complex condition which develops over years and decades, and so the plaques themselves made up of multiple parts here. So this is basically, you might get areas which have a lot of fat, areas which have less fat, and then some calcifications, that is, bits of calcium. Basically, all stuck inside the walls of your arteries. And that's what we're looking at. So this is an example of a scan. This is the human carotid artery, which is basically you're looking at this region here. So the blood comes out from the heart. So this is the heart is here, and the brain is here. It's upside down. Yeah, so here you can see this is the inner wall of the artery. This is the outer wall, and these are the calcifications. And if I go down, and also this stuff is just noise in the data. And that is the plastic tube which they use to hold the sample. Because obviously these plaques can't be scanned inside a person; they have to be surgically removed first. So if I slice it down, you see, so there's actually a lot of calcifications here. And so I've been told that this is actually an example of a dangerous plaque. So one which might rupture and send these bits of calcium into your brain. And of course, when we get down here, you can see how this part of the artery is basically blocked. I think ultrasound results have confirmed this is something like 95% blockage. So there's really not much blood going towards the brain in this case. Okay. So basically, I've shown you these images, and you know, they may look nice, they may provide some information. So you might be able to see where the walls are, where the calcium is. But essentially, this is still me artificially assigning colors. So remember how I've said before that CT works on density. Well, this is the same thing. It's me guessing and saying, well, this looks reasonably dense. So this is likely the wall of the blood vessel, and that looks very dense. So this is calcium. So basically, this is sort of like educated guesses. You use your knowledge of human anatomy, or in my case, lack of knowledge, and introduce images like that. And of course, that's what doctors like radiologists are trained for. So they're trained to recognize what these changes in density mean. But spectral imaging, in fact, allows us to get the information of the chemical makeup of the tissue. So now, instead of looking at how dense something is, we're looking at what it's made of, at the actual chemical structure. So for example, here this is all the same. These are all the same slice through this plaque. But here, for example, you can see there are dense bits of calcium here, and here you can see how there's no fat. It's because the calcium is in inside of these holes. So we can do the same thing as we do with density information. We can load these and use volume rendering to visualize them, either separately or at the same time. Like so. This is what just calcium looks like. And then you can overlay calcium on top of fat. And so you can see how there's this big fatty region here. And then there's bits of calcium stuck inside it. And you can do the same with water and calcium and so on. Or you might then choose to combine all three of these. Let's see, where's the video? This is slicing through the stomach. So remember, this is towards the heart, and that's towards the brain. And then you go fat, water, mixture of both. So these pink areas are a mixture of fat, water, and calcium. Now, and another one is very similar. So this time we have fat here and water on the inside, and calcium is shown in green. And once again, that is the tube, which is made of plastic, which in fact has the same density as fat, which is why here it shows up as fat. Okay, so in this case, that's towards the heart, and up here is towards the brain. So you can see how the artery splits. So that's called a bifurcation. Two branches going. All right. So that's the kind of visualization that we do. And the software to do it is called Exposure Render. Basically, it's an open source piece of software which is licensed under the BSD license. So we're using it, but anyone else can download it and have a look. So basically, this is software for volume rendering, which is quite general. So I've been modifying it to support spectral data and also material data. So here on the left-hand side we have the transfer function. So that's the mapping. How your grayscale values go to color. And here you've got your slicing planes. So how to slice the image from various points of view. With your brightness controls, and the quality is controlled here. So the software, as you can see, produces some very nice results. But the one thing it doesn't have is specialized tools. So currently we have that. But, ideally, any kind of software for doctors or biochemists wouldn't include tools for selection and measurement. And now, if I give you an example, it might be something like biochemists might be looking at how much fat calcium is inside of this little volume of space, and then the software should be able to tell us that. So these are the kinds of things which I'll be working on in the future. And also on improvements to the UI. Because as you can see here, that looks, I guess, a bit busy and complex. So the goal is to get it to a point where somebody who's not trained or not knowledgeable in computer science might pick it up and start using it. So we're aiming at basically medical doctors and biochemists. The final point is the fact at some point in the future we might look at visualizing not materials, so not calcium or water, but in fact tissue types. And now you might be looking at fat or muscle, blood vessels, bones, skin, and so on. So this is basically an extra level of classification after material data. But the overall goal is to produce some sort of software which will be easy to use, functional, but also provide high visual quality. So at the moment we're partway there. We've got the start. Now, yeah, so this has been a brief overview of medical imaging, CT, and then a bit about volume visualization. And then if I do any more seminars like this in the future, I might cover some more advanced estimates. But yes, any questions?